Okay, so what did we do at the end of class last time?
We're looking at the graph and determining the maximum values, minimum values, and kind of whatever other values were listed on that slide.
Yeah, and that's going to be very important. If it's one of those concepts that's the first time you see it, you're like, oh, it's pretty simple. I kind of just point at pieces of the graph. Here's where X is 3. Here's where Y is 5. I can draw a line. But historically, that is a question on the exam that a lot of people, I think, because it seems simple, I wouldn't say it's simple, but it seems simple, they kind of forget to study that and then lose a lot of points because there's a lot of questions I can ask you about that graph. So make sure you have that concept locked down. And that's what we're going to kind of continue today. So that's section 3.3, I believe. No, 3.2. I think it's 3.2. And so the rest of 3.2 is we kind of talked about the graph identifying pieces of information. And now we need to talk about a concept of increasing, decreasing, and local min and local max. And so these are also something that I don't know what age to put on this, but essentially probably someone in middle school, you could give them this graph and say, where's your graph increasing? And they could be like, there. And it's decreasing there. So on the surface, it's not too bad of a concept. This one's probably increasing. Let's draw from, blue's not a good color, from, well, it's going up from here to here. And then it's going up from here to here. So that is certainly where it is increasing. We can see that visually. We kind of always think about increasing and decreasing left to right. So imagine someone walking left to right, they are going up. So the graph is increasing. Oh, they'd start tumbling here. And now they're going to go back up and it's increasing. The issue, or why this becomes a little bit tricky, is we have to describe the situation. So we can't just say, oh, at that point in the graph, it's increasing. You can't just point at it because, well, on the exam, I won't be there for you to point at it. So I have to describe it, and I'm going to describe it in interval notation. So what are the values? And we're going to talk about all of the X values, not just like the point -30 or the 0.03. What are all of the X values where my graph is increasing? And again, X values, I want to talk about my left to my right. I'm not talking about my up and down. Maybe looking at this left part first. What's the smallest X value at the start of my increase?
-6.
Yep. So I would do -6. That's not in my... comma, and then where does it stop increasing, at least in that section?
2.
2, yep, it goes all the way up to 2. Great. And I'm going to put parentheses around that, which seems kind of weird because you might argue, oh, it's continuing to grow up to that point, and it does touch that point. That is absolutely true. But what am I trying to do? I'm trying to do 3 things at once. But it doesn't really, if we look at that top point of the graph, it starts to change, right? Like it starts to, that's where if you're kind of on the roller coaster, it goes up, 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 and then at that moment stops. And so at that moment, it's about to start decreasing. So we don't say, oh, it's still increasing at 2. We say, oh, things are about to change. I don't really know if that's where it's technically decreasing or it's technically increasing anymore. So I'm going to put a parentheses. So anytime you see increasing or decreasing questions, parentheses, no brackets. Okay. So that's the left part of my graph. Someone maybe besides John describe the right side of my graph where it's increasing.
From 8 to 11.
want to describe this portion of my graph? What's the smallest x value? What's the biggest x value?
8 to 11.
11 is the biggest. What's the smallest? Or did you say the smallest?
8.
Yeah, perfect. Okay. My volume's a little low, I guess. Yeah. So smallest value for x, again, we're talking about x, it goes 8 to 11. So that's increasing. Where's my graph decreasing?
At 2, 4. That's where it starts to decrease.
Yes, starts at 2 because we're only talking about the x value. So it starts at 2. And again, these aren't points. They look like points, which is kind of confusing about interval notation, but they're intervals. So my interval of decrease starts at +2 and goes all the way up to what?
8.
8. And there's nowhere else where my graph is decreasing, so that's it. Everyone good with that? Cool. So there's one last thing that can happen, and it doesn't really happen on this graph, but let's say hypothetically, if instead of going down, my graph levels out here. We say that's constant. So anytime you see a level part of your graph, we call it constant because, well, it's not really increasing, it's not really decreasing, it's staying the same. So that's the other thing we can ask you. Generally, we say just increasing or decreasing, but a graph could also not change. So that is called constant. Cool. So now moving into this concept of local min, local max, absolute min, absolute max. So let's actually start with the absolutes because that is, again, probably the more intuitive. So this is something that I would argue as well, that I could give a question saying, what's the highest point of the graph? What's the lowest point of the graph? That's what we talk about, the absolute max, absolute min, that someone could kind of just point at and be like, that's the highest point of my graph. So what is the highest point of my graph?
4.
Yep, 2, 4. And the smallest point of my graph, my absolute min.
-6, -3.
Mm-hmm. Nothing too shocking here, and nothing to really overthink. You're thinking about the highest point and the lowest point. Now to throw a wrinkle in it, because that's kind of what I like to do. If I have something like this, that if my graph keeps going down forever and ever and ever, I don't technically have an absolute minimum. So if I have an arrow going down, I don't have an absolute minimum because, well, I need a point. I need a point to have an absolute min, a -6 or -6 comma -3. If it goes all the way down to -infinity, well, -infinity is not a value. It's kind of a concept we approach. And so that's just something to be aware of. I wouldn't be super worried about that for the upcoming exam, but it might show up on the final and might show up on things outside of class. So just know that you're not guaranteed to have an absolute max. You're not guaranteed to have an absolute min.
So on a question that asked for an absolute minimum, if it had an arrow, would we just write that it doesn't have one? Or?
Yeah, you're just writing none.
Okay.
Yeah, or no absolute min as well. Yeah, good question. Now, the concept that is a little bit trickier to some people than absolute max and min is, well, absolute max and min, you can point and say, oh, there it is. That's the highest point. That's the lowest point in my graph. I found it. With a local max and a local min, we're now talking about kind of the highest point of the stuff around it. If you're feeling fancier going into calculus, we call it neighborhoods. And so that's the technical definition. The simpler definition of local max and local min is we kind of think about hills and valleys. And so if my graph starts to go up, 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 and then starts to go down, this is where that change happens. At the top of that hill, that's my local min. same thing with local, or no, sorry, that's my local max. Local min is, we could kind of think of it as a valley. My graph is going down, 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 and it's turning back up. So this would be a local min. And now what's interesting about local mins and local maxes is we can have multiple of them. If I have a graph that looks like this, up, down, up, down, up, down, up, down, well, all of these points are going to be local maxes. That one is, that one is, that one is, that one is. So that's something to be aware of. I think this graph has just one local max, one local min, but that's not always a limit. You can have a ton of hills, you can have a ton of valleys. So that's something to watch for. So what are my local, or slash is my local maximum in this graph? Kind of already helped you and circled it and everything.
Local max would be 2, 4.
Local min?
Be 8, -2.
And -6, -3.
Yes, I'm very glad you said that. So in order for something to be a local max or a local min, we think again about a valley. And I would argue that yes, this is an absolute min because it's the lowest point on the graph, but that's not a valley, right? A valley would kind of dip and then come back up. So endpoints can't be local maxes or local mins. So I'm glad you brought it up. I would say that as well. I would argue like, oh, that's a local min. It's the lowest part in the graph at that point, but we need to kind of have that come back up. Any questions about this? Cool. So when you're reviewing, I'll double check this before I put you in your breakout rooms. When you're reviewing, if you want to make sure you have this concept locked down and the concept that we worked on last class, the worksheet 3.2 would be a good starting point. Okay. One more concept and then I'll put you in breakout rooms. This concept of even, odd, or neither. Now this concept is actually gonna feel hopefully a little bit nice because we've essentially done this. We used different terms when we saw it the first time. We called it symmetries. We had symmetry about the X, symmetry about the Y, or symmetry about the origin. And the tests we did there are very similar to what we're going to do here. There are two key differences. One, it's either even or odd or neither. So if it passes one of the tests, you don't have to do any of the other ones. It's not going to be even and odd, and well, neither one really make any sense. So that's one, the biggest difference. And two, I won't have symmetry about the y-axis. I wouldn't consider that with functions. Why? Does anyone know why I couldn't have a function that is symmetric about the x-axis? Sorry, the x-axis, this vertical symmetry.
You'd have an X output with 2 Y outputs.
Exactly, it's not a function. And so that's why we don't really consider it when we're talking about functions, because they're not functions. Okay, so the tests are if something is even, then my f of x is going to be equal to my f of negative x. If something is odd, then my negative f of x is equal to my f of negative x. And then otherwise, if it fails both of those tests, we say neither. And so this process, we might note here that this guy, this f of x or f of negative x, shows up in both tests. And so my very first step is to find f of negative x. So for question 1, how do I find f of negative x?
You'd replace X with negative X.
Mm-hmm.
And see if it equals.
Yeah, so I replace my x in this equation with negative x, just like we did with the symmetries. And then I simplify. Well, negative x squared is just x squared. Cool. And then as Austin mentioned, now that I found my f of negative x, well, the test says I should compare this back to my original function. And lo and behold, they are exactly the same. F of x squared, even. And now, as I was saying, that if this was a question about symmetries, I would have to keep going. I would have to test to see if there's some symmetry about the y-axis and then symmetry about the origin. But that's not the case with even, odd, or either. It's one of those three things. So I'm done with the question. I can move on. Okay, now I'm doing question 2. Starting point is exactly the same. I don't know if this is even, odd, or neither, but I know f of negative x is kind of a crux of both of these tests. So I find f of negative x. I plug in negative x into both of my inputs, both of my x values. Oops, that shouldn't be equals. And that should be 5. Crushing it today. Yep. And then, well, negative x to the 5th is, well, it's just negative x to the 5th. It's not going to become positive because it's not an even power. And negative x is negative x. Not a whole lot of simplification to be done here. So I'm doing my even test. I always start with my even test. I compare it to my original function, original function. Oh, they're not the same. This one has a negative. This one has a positive. So it's not even. So I keep going. Type it out, but I wouldn't even write this part. I would just, if this was my exam, I would just keep going. So my next thing is to find negative f of x. How do I find negative f of x?
Would you multiply the entire original equation by -1?
Perfect. So my original equation is x to the 5th plus x. If I multiply both terms by -1, I get negative x to the 5th minus x. And now when I'm doing the odd test, notice here, I don't go back to my original function. I compare what I found in f of negative x. So in this equation. So I look at this guy and say, does this guy compare to this guy? Well, not only does it compare, they are equal. They are exactly the same. So I say it's odd. While I'm thinking about it, I probably mentioned this already, but on the exam, I sometimes become not very good at guessing what your final answer is. So somehow indicate to me what your final answer is. In this case, well, even. I always box my answers. You don't have to box it. Some people like to underline. There's many different ways to indicate it, but tell me somehow that's your final answer, because I don't like looking at a paper with a ton of work and then saying, oh, I don't know what your final answer is. I'm going to guess this one. That's probably not the right answer. So make sure that you give me good reason to pick the right one. And that's the whole process. That's what we're going to do is if it lands on that even case, we're done. Good job, us. If we go through and it's not even, well, we test to see if it's odd. And if it's odd, great. Good for us. Box that answer. If this fails to, if the negative f of x is not equal to f of negative x, well, then we see neither. And kind of spoiler alert, that is what happens in this last case. So I have a g, but really function name doesn't matter. The process is exactly the same. So g of negative x Well, it's just negative x plus 1. That's not my original function. Okay. Negative g of x. Multiply my function by negative 1. Compare it to not my original function, to the g of negative x. Not the same. So it's not even, it's not odd. This is another good example of questions that if you just write the answer and show no work, I'm not going to give you any credit. I'm very generous with partial credit, but these are questions that there's a 1 in 3 chance of you getting it correct. So if you just guess, well, it clearly shows me you don't know how to do the tests, and so I'm not going to give you credit if you magically get it right. So make sure you're showing your work on this question. Make sure you're showing your work on any question. Again, I'm very generous with partial credit. Cool. Any questions about this? Any questions about any concept? Because this is the end of content. The rest of the class is review. Cool. Let me pause. So I'm going to stop the recording.